Today we are here with the module 2 of the chapter 2, which is electric potential energy. So let's begin this. First of all, we have electric potential energy of a system of 2-point charges. Let us consider a system of 2-point charges plus Q and Q naught separated by a distance r. We will consider that we have brought this system of charges from infinity to the present location. So when we bring this from infinity to the current location, then we have to do some work, and this work is stored in the system of charges as electric potential energy. So we will find out the work done in this case in the same way as we have derived in the case of electric potential due to a point charge. So that work done that we need to do while bringing this system of charges from infinity to the present location is stored as electric potential energy. So we will define this. The work done to bring two charges from infinity to their present location is stored in the system of charges as potential energy, which is called electric potential energy. Now, how to derive this work done or electric potential energy? Let's see. First of all, we have to find out this force of repulsion between plus Q and Q naught. That will be given with the help of Coulomb's law. The electrostatic force between plus Q and plus Q naught will be given as F is equal to 1 upon 4 pi epsilon naught Q naught upon R square. Now we will find out the small work done for the small displacement, and that will be small work done to move the charge Q naught by a small distance dr is dw is equal to fdr cos 180. Why cos 180? Because the angle between the force and the displacement is 180, because this f and dr both are opposite to each other. That's why the angle is 180. The value of cos 180 is -1. Put the value and we will get dw is equal to minus fdr. Now we will put the value of f from equation 1 to this expression. So put the value of f from equation 1 to this expression. We will get dw is equal to minus fdr. So put the value of f and we will get dw is equal to minus 1 upon 4 pi epsilon naught q naught upon r square into dr. So this is the work done for the small displacement dr. To calculate the total work done from infinity to r, we have to integrate this expression. So let's integrate this expression. Integrating, we get this integration 0 to w dw is equal to minus 1 upon 4 pi epsilon naught and q naught. These are constant. Integration infinity to r of dr over r square. This dr over r square, we can write this r square in the denominator. When we take this in the numerator, it will be r raised to the power minus 2. So this will be integration 0 to w of dw is equal to minus 1 upon 4 pi epsilon naught q naught integration infinity to r raised to the power minus 2 dr. So we will integrate this with the help of the formula adding 1 in power dividing by new power. So this would be like the integration of dw will be w limits 0 to w minus 1 upon 4 pi epsilon naught q naught as it is, and here adding 1 in power dividing by new power, and the limits lower limit infinity and the upper limit r. Now we will solve this one. The power of r is minus 2 plus 1, that becomes minus 1. So we will have this r raised to the power minus 1 and in the denominator minus 1. This minus 1 when multiplied with this negative it becomes positive, and we get this plus 1 upon 4 pi epsilon naught q q naught, and this r raised to the power minus 1 can be written as 1 upon r. Now put the values of limits to solve the expression. Alright, put the upper limit, that is w, minus lower limit, that is 0, and here 1 upon 4 pi epsilon naught q q naught as it is. In the place of r, put the upper limit, that is r, so it becomes 1 upon r, minus put the lower limit, that is infinity, so it becomes 1 upon infinity. The value of 1 upon infinity is 0, so this becomes w is equal to 1 upon 4 pi epsilon naught q q naught into 1 upon r minus 0. So this expression will be like this: w is equal to 1 upon 4 pi epsilon naught q q naught upon r, and this is the work done that we need to do while bringing the system of charges from infinity to the present location, and this work done is stored as potential energy. Watch. W is equal to 1 upon 4 pi epsilon naught q q naught upon r. This work done is stored in the system of charges as potential energy, that is electric potential energy, which will be given as U is equal to 1 upon 4 pi epsilon naught q q naught upon r. This is the expression for the electric potential energy of a system of 2-point charges. Now, if there are 2-point charges q1 and q2 separated by a distance r12, then the electric potential energy of the system will be given as like this: U is equal to 1 upon 4 pi epsilon naught q1 q2 upon r12. Now we will move to the electric potential energy of a system of 3-point charges. Let us consider a system of 3-point charges q1, q2 and q3, which are separated by the distances r12, r23, r13 respectively. Now, what will be the electric potential energy for this system of charges? Let's see. It will be given as the algebraic sum of all the electric potential energies for individual pairs. So for the pair of q1 and q2 separated by a distance r12, the potential energy will be 1 upon 4 pi epsilon naught q1 q2 upon r12. For the pair q2 and q3 separated by a distance r23, the electric potential energy will be 1 upon 4 pi epsilon naught q2 q3 upon r23. In the same way, for the system of charges q1 and q3 separated by a distance r13, this pair will include an electric potential energy of 1 upon 4 pi epsilon naught q3 q1 upon r31. Let's sum them up to calculate the total energy, the total electric potential energy. We can take this 1 upon 4 pi epsilon naught in all the three terms as common, then we will get this: U is equal to 1 upon 4 pi epsilon naught q1 q2 upon r12, q2 q3 upon r23, q3 q1 upon r31. This is the electric potential energy of a system of 3-point charges. Moving ahead, we have electric potential energy of a dipole in electric field. So here we have an electric dipole of charges negative q and plus q separated by a distance 2a in an electric field E. If we need to rotate this electric dipole in the electric field, then we need to do some work, and that work will be stored in this dipole as potential energy, and we will call that electric potential energy. So what we are saying? We are saying that the work done to rotate a dipole in uniform electric field is stored in the dipole as potential energy, which is called electric potential energy. So we need to find out the work done for the rotation of this dipole. First of all, we know that the torque or the moment of force or the moment of couple experienced by this dipole, we already know that is the torque experienced by the dipole in uniform electric field is tau is equal to Pe sine theta. Now we will calculate the small work done for the small angular displacement. Take this as equation 1. Now, the small work done to rotate the dipole by a small angle d theta is given as this. dw is equal to tau d theta. Once we have find out the small work done, then we can calculate the total work done by integrating the expression. Watch here. The work done we know that is force into displacement. In this case, this is the moment of force or torque. That's why we need to take the displacement, which is angular displacement. Now put the value of tau from the equation 1. From the equation 1, we have put the value of tau, which is Pe sine theta. dw is equal to Pe sine theta d theta. This is the small work done for the small angular displacement. Now the total work done to rotate the dipole from theta 1 to theta 2 will be given as this. Integration 0 to w of dw is equal to theta 1 to theta 2 Pe sine theta d theta. P is the electric dipole moment, which is constant since 2a is constant and q is constant. Electric field is uniform, that is constant, and we need to integrate only this expression, which is sine theta into d theta. Alright, the integration of dw becomes w. Watch here. The integration of this dw becomes w. Limits 0 to w. Pe as it is, and the integration of sine theta becomes minus cos theta, and the limits theta 1 to theta 2. Take this negative sign outside the bracket and we will get this. W limits 0 to w is equal to minus Pe cos theta limits theta 1 to theta 2. Now put the limits. In the place of w, put the upper limit w minus lower limit 0. So this becomes w minus 0 minus Pe as it is. In the place of theta in cos theta, put the value upper limit, which is theta 2, so it becomes cos theta 2 minus the lower limit, it becomes cos theta 1. Take this negative sign inside the bracket, so it will become w is equal to Pe cos theta 1 minus cos theta 2. This is the work done that we need to do while rotating this electric dipole in uniform electric field. This work done is stored in the dipole as potential energy, that is electric potential energy, which will be given as U is equal to Pe cos theta 1 minus cos theta 2. So this is the expression for the electric potential energy of a dipole in uniform electric field. Moving ahead with some more, we will discuss about conductors and insulator. So let's see here. In case of the insulators, there are a very few free electrons or no free electrons at all. In case of conductors, there are so many free electrons. So we will say that insulators are those substances which do not have the free electrons to conduct the electric current, but the conductors are those substances which have the free electrons to conduct the electric current. So watch here. Conductors. The substances which have free electrons to conduct the electric current are called conductors. For example, copper, aluminium, silver, iron, etc. Now come to insulators. The substances which do not have free electrons to conduct the electric current are called insulators. For example, wood, glass, plastic, rubber, etc. Further, we will discuss about free charges and bound charges in a conductor. So let's see. Here you can see an atom, here the nucleus, and the electrons are there in the different shells, and this is the outermost shell. Alright, this is the condition in the absence of electric field. There is no external electric field present here. What will happen if we create an external electric field here? The electrons from the outermost shell will be detached from this atom and will be moving freely and will be called free electrons. So let's see. We create the electric field. This is the positive plate and this is the negative plate. The direction of the electric field is from positive to negative. What will happen? The free electrons or the electrons from the outermost shell will move to this positive plate or in the direction opposite to the direction of the electric field. So these electrons which are detached from the outermost shell are called free electrons or free charges, and these other shells are nearby to the nucleus or the positive charge which are attracted by this nucleus or the positive charge. So these are bound electrons or the bound charges due to the positive charge of the nucleus. This positive charge is not affecting that much to the outermost shell's electrons. So these will be detached easily and will be called as free electrons when in the presence of external electric field. So we will say in metallic conductors, electrons of outermost shell of the atoms are loosely bound to the nucleus. On applying electric field, they get detached from the atom and move freely inside the metal. These free moving electrons are called free charges. The positive charges consist of nuclei and electrons of inner shells are held stationary. These immobile charges constitute the bound charges. So immobile charges, we are talking about other shell charges other than the outermost shell, which are nearby the positive charge of nuclei. Now we have dielectrics and electric polarization. So what are these dielectrics? Dielectrics are nothing but the insulators. Dielectric is another name for the insulator. So insulators are called dielectrics. Now, when dielectrics are placed in an electric field, practically no current flows in them. Why? Because they don't have free electrons, because they are not conductors, they are insulators. So they don't conduct the electricity, they don't conduct the electric current because they don't have loosely bound or free electrons. So what happens when they are placed in electric field? They don't conduct the electric current. Instead, electric polarization occurs. What is this electric polarization? We will discuss here. Let's see. Here we can see an unpolarized material in which the positive and negative charges are randomly distributed. There is no a certain order of the positive and negative charge. But when we introduce an external electric field here, then what happens? The negative charges, all the negative charges are minutely displaced towards the positive charge. All the negative charges minutely displaced towards the positive charge, and all the positive charges are minutely displaced towards the negative charge. So they create an order like this: positive, negative, positive, negative, positive, and negative. Now, this dielectric material will be called as polarized by an applied electric field. So, how can we define polarization? Let's see. The positive charges within the dielectric are displaced minutely in the direction of electric field, and the negative charges are displaced minutely in the direction opposite to the electric field. This slight separation of the charge is called polarization, which reduces the electric field within the dielectric. That's all for now. See you again. Thank you.